Hi method students, welcome to the last exercise of chapter 10. This exercise is a little bit of an unusual one. It's called families of functions, and it's basically just about graphs where, or situations where you have a function with an extra parameter, an extra unknown in it, like an a or a k or a b or a c. And what you might be investigating is what's going on as that value of a or b or c or k changes, and how that produces different graphs. So, for example, if you had the function ax squared, depending on your value of a, you've got an infinite number of different parabolas that are possible to be produced by that function, right? They would all go through 0, 0, but for positive a values, you're getting all these potential positive parabolas. For negative a values, you're getting all these upside down ones, right? And obviously, if you throw in a plus k, where k can be any number, then you've also got parabolas sliding up and down and all that sort of thing. So this section is just really about practice with questions that have the extra unknowns thrown in there. And remember, don't be thrown off by them. You can still apply all the skills that you have that you would normally apply if they were just numbers. Don't be scared off by the fact that they're letters, okay? So we've just got one example in this section. We're told the graph of y equals x plus a squared times x minus b squared has 3 stationary points. Now, if you're really not sure if the a and the b is really throwing you off, you can imagine that a is just like a number and b is just a number. So if you said that a was equal to 5 and b was equal to 3, you could rewrite this equation and hopefully recognize that all this is going to be is a quartic graph, because you've got x to the power of 2 times x to the power of 2. It's a positive quartic graph, so we know that positive quartic graphs can look like that sort of W type shape where we get the 3 stationary points, okay? And we also know, if we're being asked to find coordinates of stationary points, that we can differentiate and let the derivative equal 0. So let's do it. dy dx is equal to, now this is a product of two functions, right? So I'm going to use the product rule here, and the way I think of the product rule is you put down the first thing times the derivative of the second thing. Now the derivative of that second bracket squared, if we differentiate the outside, it would be actually, no, sorry, I usually think of it as differentiate the inside first. So the derivative of the inside would be 1, which obviously isn't going to do much, times the derivative of the outside, which is going to be 2 times x minus b to the power of 1. Plus, put down the second thing and differentiate the first. So x minus b squared times the derivative of the first, and the derivative of the inside of the bracket is 1, times differentiating outside, we get 2 times x plus a to the power of 1. All right, so dy dx is equal to, let's tidy all that up, we've got 2 x minus b x plus a squared plus 2 x minus, let's say x plus a x minus b squared, right? And for a stationary point, so that's dy dx, for a stationary point, we know that all that will equal 0, right? Now, if we're trying to solve this for x, to find the coordinates of the stationary point, well, we can look for some common factors to take out. And there's actually, we've really only got 2 terms here, and there's lots of common factors within these terms. We've got 2, and then like 1 of each bracket, right? Because both terms have at least one of the brackets in them. So I've got an x minus b and an x plus a as a common factor of each term. Just going to take that out, and let's have a look at what's left in each term. I've got 1 factor of x plus a left over in the first term, x plus a, and I've got 1 factor of x minus b left over in the second term. All right, so now that we've got that factorized, we can actually apply the null factor law. And so from each of these sort of sets of brackets, we get a potential solution. So x minus b equals 0, which of course means x equals b, or x plus a equals 0, which of course means x equals negative a, or this square bracket, which is, well, I'm going to sort of do 2 steps in one here. If I add it all together, 2x plus a minus b equals 0. which would mean that x equals, add the b, subtract the a, divide by 2, we get b minus a over 2. Okay, so a little bit squished there, but you can see we were only asked to find the x coordinates, so we've got x equals b, x equals negative a, and x equals b minus a over 2. Those are the 3 coordinates of our stationary points. All right, so if a equals b, determine the x coordinate of the local maximum. Okay, now at this point, we're going to kind of do what arguably we should have done at the start and kind of use our knowledge of what this graph looks like to kind of draw a sketch, at least in terms of a and b, okay? Because one of the problems here without the picture is that we're not really sure which of these would be the local maximum. But we did say at the start, this is a positive quartic graph, all right? So if we've got an intercept at, let's say, negative a, and another intercept at b, and this third intercept somewhere else, well, our graph kind of, we know that a quartic graph has got to be going up at both ends. And so really what's going on here is we've got a turning point there, and we know that it's a turning point because this was a squared factor, okay? We've also got a turning point at b on the x-axis, again because that was a squared factor. And so really the maximum's got to be somewhere in the middle, right? Because this is turning around, that's turning around. I have to have a maximum somewhere in the middle here for this graph to be possible and make any sense, okay? Which means probably we could have worked out the values of a and b sort of a little bit more quickly just from using the graph as knowing that they were coordinates of stationary points, but we still had a bit of work to do to get this other stationary point anyway, so we still would have had to differentiate in part A. Okay, now this is saying if a equals b, and there's 2 ways you can think of this. If a is equal to b, then these 2 stationary points, these 2 minimums, are going to be an equal distance on either side of the y-axis, which means we need to actually have a symmetrical graph. And if we've got a symmetrical graph, even though my sort of wonky looking thing doesn't look like it, the maximum must be in the middle, which means its coordinate must be 0. Or you could actually say, okay, well, now I know that the x equals b and x equals negative a, they were minimums, so this is my maximum. I can look at that and say, well, if b and a are equal, then this is just giving me x equals b minus b over 2, which is 0 over 2, which is 0, right? And so there is, yep, the x coordinate of the local maximum is x equals 0, if b and a are the same number. Okay, so again, just one example of working with unknown a's and b's, but as you can see through this example, there's still a fair bit we could apply the same way we would if this equation had said x plus 2 and x minus 7. Okay, so don't be thrown off by the extra unknowns that are thrown in. Most of your techniques will still work, and quite often, you know, that's the way to solve these problems. And sometimes you do just have to start with writing down a first step and seeing if that leads you to a second step, and then you're off and running. As always, good luck with your questions. Ask your teachers for help, and I hope this video was somewhat helpful. Cheers.